Good morning. Well, the question we have today is from Michael Lamancusa. I hope I pronounced that correctly. And it's actually not about quantum computing. In future, I want the questions to be about quantum computing because this is a quantum computing group. And the topic of quantum computing is so exciting at the moment. I don't know whether you got my posts, but one, quantum supremacy has been reached, and that's where a quantum computer actually makes a computation, it makes a computation. It's actually just generating a random number, so it's not a computation, but it doesn't matter. Faster than a digital supercomputer would. And that was only last month with Google NASA. And the other thing is, I think I text you guys sort of the Woodside have committed to quantum computing on the IBM Q experience. Now the beauty of IBM's quantum cloud basically, and with the course I do, with the first course we touch on it, but in the second course I'll actually get you ready to write your own programs on the IBM Q experience. It's a free facility, so it's fantastic. But let's get on to Michael's question, which is basically what happens when two black holes collide. So, fantastic stuff. And of course, we've actually known about, or theorized about black holes for over a century. But we now have a super detector here on Earth, which we've only had for about 15 years, there's a number of them, called LIGO. And that's Laser Interferometer Gravitational Wave Observatory. Fantastic stuff. All it's doing is, it's sort of imagine it as a big cross, which goes on for like 10 kilometers at each line, and basically the gravitational wave is captured and then sent to a mirror 10 kilometers away in two different directions, and then the signal is then bounced back to the center. So it goes simultaneously vertically and horizontally for 10 kilometers and then comes back. And then the slight difference between the two. And just to tell you how slight it is, it's like observing the sun 93 million miles away and being 1 centimeter to the left. These things are exceptionally accurate. Can measure the distance from Los Angeles to New York to the width of a hair. These things are unbelievably accurate, and we have them set up in 3 places in the States. They're actually also in India, and probably in a few other countries. I'm not sure, I haven't kept up with it. But we can detect, which we did 2 years ago, detect gravitational waves. Now, what's a gravitational wave? Einstein told us the theory of space-time, where space and time is one fabric. In his theory of special relativity, he showed that time is different for everybody. Where you are and what speed you're going at, time changes. And that's the physical process of aging and everything. If you got in a spaceship that went near the speed of light and went away for 10 years and came back, you would be physically, mentally, in every single way younger than your children. What a scary thought for you and them. But Einstein then, the natural development from the theory of special relativity was later on, in about 1915, his wonderful theory of general relativity, where space-time is a fabric. So think of it just like a rubber mat on a trampoline, and you put a great big cannonball on one end, that will cause a dent in the fabric. And then if you span a little marble, it would go round and round. The marble thinks it's going straight, but it's actually going round and round the gravitational pull of the cannonball. And it's the same in the real world. So what Einstein in 1915 postulated that number one, light would bend around the sun, and in the famous Eddington expedition where they went to somewhere in South America or South Africa, and they viewed the eclipse, and they proved that when there was an eclipse, they could see the star behind had slightly changed shape, and that was because it was bending around the sun. When two holes collide, Einstein said it would cause such movement in the fabric of space-time that we would be able, well, in fact, he never even thought that we could measure it, but he just postulated a Duncan experiment, which is a thought experiment. He just said that's what will happen. How do these people do it, you know? He just said this is what happened, it has to happen. And he honestly didn't think that we would ever have the machinery that could actually measure it. But now we can measure it quite accurately. And by the way, they're building a new LIGO in space. It's called Stellar, and it should be ready in about a year or 2 years. And what that actually does is, instead of just being restricted to 10 kilometers and having to have no interference in between that 10 kilometers, so it's very controlled. Out in space, you don't have to worry about that, and it's literally going to go, you know, about the distance from here to the moon and back. So the measurements are going to be even more accurate, believe it or not. But Michael's question is very relevant, because there's just been a recent spotting of two black holes on a collision course. They're 2.5 billion miles away. So the light from them has taken 2.5 billion years to reach us. But they're only 1,400 light years apart, which obviously is a light year is a distance, of course, the distance light travels in a year. They're 1,400 light years apart, which seems like a long way, but it isn't in astronomical terms. By the way, black holes never actually collide, although we don't really know, because it's a very, very rare event. But the hypothesis is that the black holes, as they near each other, the gravitational attraction of energy within the two causes them to give up energy, and then there comes a time when they have no more energy to give up. So they start orbiting each other, and that's called, when the nearest they can get to each other is 3.4 light years, I think it is, which is 1 parsec. So it's called the final parsec problem. That is that they never touch it, but we really don't know, because it's very, very rare to see two black holes colliding. We were very lucky a couple of years ago. A black hole, by the way, is normally 4 million times the size of the sun. And of course, we all know what a black hole is. It's where light can't escape. Imagine if you throw a ball up here, well, it will soon come back down to Earth because of the gravitational pull. So to get away from that, you'd have to throw it at 11 kilometers a second. You'd have to be very strong to get out of Earth's orbit, Earth's gravitational pull. Obviously, if you shone a light upwards, it would just carry on, because it's 300,000 kilometers a second. But in a black hole, even the light, even at 300,000 kilometers a second velocity, it cannot escape. It's called the escape velocity. It cannot escape the pull of the black hole, so that's how strong it is. It's immeasurably strong. And these two, well, a normal black hole, there's a supermassive black hole in the center of every galaxy, including our own. It's called Sagittarius G star. and it's about 14 million times the size of the sun. Think about that for a few seconds. But these two black holes that are colliding 2.5 billion light years away, they're a million times the size of Sagittarius G-star. It's incomprehensible. And the effect on space-time will be, if in fact, the problem with LIGO is that the ripple in space-time is going to be more like a tsunami instead of a ripple. These things are absolutely huge. Problem is, of course, light's taken 2.5 billion years to get here. We can't wait 2.5 billion years to see it happen. It probably has already happened, and a huge tsunami gravitational wave is on its way to us. I mean, black holes are obviously amazing things. Conspiracy theory believes us to think that if the black hole is infinite, then the bottom of the black hole links up with the bottom of every other black hole. So it does, get a bit crazy. So that's what happens when they actually collide. Michael, they actually don't collide, but they go very close to each other, 3.4 light years away. That's how close they tend to get to each other. But again, this is just theory. But it's all very exciting and very exciting times. And I hope that's answered your question. Thanks, Michael. Back to quantum computing questions. Now, Kieran, my brother, my wonderful brother, asked a great question about how much energy does it take. I hadn't even thought of that. I'm supposed to be in renewable energy as well. Everybody thinks I'm a real greenie and real into renewable energy. My brother Kieran is 100 times more renewable energy focused. In fact, ran the largest solar company in Perth for about nearly one of the top three, which I worked for a decade or so. I don't know. I have no idea. I haven't thought about it, but I will research it. It must be a huge amount because, as we all know, or should know now, the qubit, which is on a photon or an electron, either can be used to be a qubit, has to be an absolute freezing point, minus 273 centigrade, whichever one it is, 0 degrees Kelvin. So what they have to do is have these great big, what they call dilution chambers, which are dilution refrigerators, and they gradually get it colder and colder and colder until right at the bottom spec, it's the coldest place in the universe. Now that must take a lot of energy. But I will check that. I wonder what IBM, for example, are saying about their quantum computer, Google. There's a company called D-Wave in Canada which are making most of these quantum computers. And I might add, they're not fully fledged quantum computers. They're what's called adiabatic quantum computers. And it's almost like having a computer that can only do one thing and doesn't do it very accurately. The whole point with quantum computers, the reason why it's taken so long, the reason why it's so difficult, otherwise it would have been done, is quantum interference, quantum decoherence. The actual interference with the wave measured by the qubit. So in a bit you've got one on and off, but in a qubit you've got this spherical, they call it a Bloch sphere, and there's an infinite number of places it can be. So every time you put a qubit on and you entangle it and superpose it, it can access one of these infinite amounts of spaces. But if that infinite amount of space is changed because of an electron bouncing off it, then obviously the answers are rubbish. But in some cases it doesn't really matter. When you're talking about general computations, where at the moment classical computers can't even begin to solve, quantum computers can solve them to an nth degree of accuracy. But we're gradually improving, decreasing the quantum interference. Very exciting times. My ultimate objective is to get a team together who can actually write quantum algorithms, and then we can go out to industry. We can use the IBM Q experience. It's free. You just log on and use their quantum computer. For God's sake, it does things so quickly that it's never occupied. So IBM, Microsoft does the same thing, although they use a simulator. I forget what it's called. But I'm on both of them, and I will get you onto both of them. I urge you to try and get new friends to join the group. The only way I can exist and move forward is with members getting the message out there. And then my first course is free, which I like it that way because it will sort of get people to the stage whether they know whether they like this or not. It's wonderfully interesting. Everything's exciting and interesting. But if you want to actually program on quantum computers, which actually I can't, I'm not a programmer, you really have to do a lot of work. And to understand exactly how it works, you really have to understand complex and imaginary numbers, which I cover in the course, and matrices and linear algebra. And look, it's not easy. The reason why it's not easy is because it's so abstract. They're always talking about abstract things. It's the square root of -1. It's all strange stuff. But look, we'll talk about it on another day. But Kieran, I'll answer next week. I'll research and answer the question on just how much energy does a quantum computer consume. Thank you for your question, Michael. Thank you to everybody there. Please get more people to join the Quecra group. I'm counting on you. And it's for the future of our children and young people that we quantum computer. There's no question about that.